Okay, good afternoon, everyone. Welcome to today's Colloquium. It's my pleasure to introduce our today's speaker, Dr. Hartwin Peelaers. Hartwin got his master's degrees in physics in 2005 and then PhD in physics in 2009, both from University of Antwerp in Belgium. After that, he moved to Santa Barbara at UCSB as a postdoc from 2010 to 2015. And since 2015, he became an associate specialist in the material department in UCSB. But today, the topic will be limits of transparency of transparent conducting oxides. Please join me to welcome Dr. Peelaers.
Thank you very much for the nice introduction. So today I want to share some of my recent results on the limits of transparency of transparent conducting oxides. But before I start, I'd like to acknowledge my co-authors on this work. So Manos Kiapoakis, who's now at the University of Michigan, and this is work done in a group of Chris van der Waal at the University of California, Santa Barbara. And I recently learned, based on a one data point sampling, that Lawrence is only slightly cooler than Santa Barbara, so it's really great. So I also like to acknowledge the funding for this work. So it was funded by the Department of Energy, the National Science Foundation, and Army Research Office. And since this is a computational talk, I also need to acknowledge the computational resources. So those are from the NSF-funded EXCEED Supercomputer Center, the DOE-funded NERSC Supercomputer Center, and on-campus clusters from the California Nanoscience Institute. That being said, let's first discuss what transparent conducting oxides are. So the first part, transparent, is exactly what you think it means. Those materials are transparent to the visible light, very much so like a typical glass window. And typically the materials that have these properties are insulating. So you probably have one of those at your home, and maybe even several of those. So the next part is conducting. So with conductivity, I mean conducting to electrons. And the material you typically associate with that would be a metal. For example, a copper wire, or heavily doped semiconductors like silicon, which I'm showing here. But once you combine those two properties, you can really enable lots of applications. So our example of the glass windows, they're transparent, but they certainly are not conducting. At the same time, your copper wires are conducting but not transparent. So it really takes a special kind of material that combines both of those properties. And once you do, can enable lots of applications. For example, in solar cells, you can make top contacts that are transparent to the visible light, but still can be used to transfer your electrons generated in your solar cell out of your solar cell itself, so they can do some useful work. You probably also have lots of touch screens on your smartphone and whatnot. Also there, transparent conducting oxides are really important. And the same is true for any kind of LCD screen. You need to have some material to make the electrodes transparent so you can actually see what's on your screen. And at the same time, this material needs to be conducting. So how do we do this? So it turns out that metal oxides can combine those two properties. So typically, these are wide bandgap semiconductors, and the wide bandgap enables the transparency. So let me show you a typical band structure of such a material, as I will be showing more of this in the talk. So let me quickly run you through what I'm actually showing. So what I'm showing is just an energy dispersion relationship. So on the x-axis, we have the k points in momentum space, and on the y-axis is the energy. And any line you see in those diagrams means that is an allowed state. So your electrons can be there. So typically, for these transparent conducting oxides, the band structure looks like this. So at the top, in the purple color, we have conduction bands. And usually those are made of s orbitals, which means you get this highly dispersive conduction band. And because this high dispersion, your effective masses will be low. So as soon as you add carriers to your conduction band, those electrons can really conduct the electricity well. You can almost get metallic conductivity. And in case you're wondering, it's really easy to dope those materials even to really high doping concentrations. Yes?
So for good conductivity, you want the bands to be flat?
No, you want to be them. Yeah, because it's related to the effective mass. So the more curved the bands are, the smaller your effective mass, the easier the electrons move in your material. But it's a good point. For example, the valence band in those materials, they're derived from oxygen p states. And as you can see, those are very low dispersion, which means high effective masses. So in case you would have holes in your bands, their mobility will be really low. So let's have a look at the absorption itself. So the band structure I'm actually showing is for a material called tin oxide. And this material has a band gap of about 3.6 electron volts, which means if you have a transition from any of those occupied valence band states to your conduction bands, your photon needs to have at least 3.6 eV of energy. And that also means if you absorb such a photon, this transition will not be in the visible region. But of course, like I said before, we really want to have conductivity. And in order to do that, we add free carriers to the system, which means you will start filling the lowest conduction band. But of course, once you have carriers there, those carriers can also absorb photons. They can go from the lowest conduction band to higher conduction bands. But in this material, because of this large dispersion of the lowest conduction band, this energy difference is also large, in this case 4.7 eV, which means if you absorb a photon, it's also not in the visible region.
But if I go to the left, then the gap gets small.
Yes, so if you have really high carrier concentrations where you really fill the bands, you might have these additional transitions. But as I will show you in just a few minutes, you don't actually need to have these high carrier concentrations in order to have absorption. Because if you want to have absorption in the visible, you need to be able to go to any of those states which I indicated by this rainbow of colors. We just give you an idea of the energies of the visible light. But as you can see, there's no direct transition into this region. There are no bands there, so there are no states. So in order to do that, you need to have some process that gives you a bit of momentum so that you can go to a final unoccupied state either in this region or in this region. And one such process is given by the phonons. So if you scatter with phonons, you might be able to reach a final unoccupied state, which will reduce your transparency. And these kind of processes, if you open a textbook, you probably have seen them being described with a Drude model, typically fitted to experiment to explain this kind of absorptions. But we want to do better than a Drude model. We really want to study this from first principles. So how are we going to go about that? So in order to do that, we will calculate absorption coefficients explicitly using Fermi's golden rule. And I've given the formulation here. So this has a typical form you expect from Fermi's golden rule. You have a sum over initial and final states of some matrix element to the square. And then you have some density of states, which is given by this delta function. So let's go through this formula step by step in order to really understand the different factors in this. So first of all, if your material is not isotropic, it means your absorption will depend on the direction of the incoming light. So we need to take into account the polarization of the light. So the next term we have is this generalized optical matrix element. And the way to think about those is schematically depicted here. So if you go from an occupied state, you can first absorb a photon to some virtual state. And from this virtual state, you can scatter with a phonon in order to reach your final unoccupied state. So that's given by the S1 process. And if you look at this formulation, you see exactly the same thing happening. So you have a dipole matrix element that signifies your absorption to the virtual state. Then you scatter. Then you couple your electron to a phonon with the electron-phonon coupling matrix elements, which are given here, which will bring you from K to K plus Q, which is your final state. But of course, you can also do the opposite process. You can first scatter with a phonon to a virtual state, and then from the virtual state, absorb a photon to end up in your final unoccupied state. So the next term we see is this P factor, and this is just taking account of all the different occupations. So we have the phonon occupation factor and the electron occupation factor. And the latter just takes care that you start from an occupied state to an unoccupied state. Because if you don't do that, you can't have any absorption process. And finally, we have this delta function, which you can think of as the density of states, which ensures that we conserve energy in the whole process. You might have noticed that some of those terms have both plus and minus signs. And that's because there are two different processes you can have. You can either emit a phonon or you can absorb one. And both of them will lead to the absorption of a photon. So you need to take into account both of them. So if we can calculate all of those parameters in a way where we don't use any fitting parameters, we really have a predictive theory. But before I go into more in the computational details, let's have a brief discussion about this electron-phonon matrix element, because maybe not everyone is familiar with this. So a very convenient way of thinking about this is in a polar material. If you have a polar material where you have ions of the opposite charge, and you have a longitudinal optical phonon in this. So what will happen is that your ions will move in opposite directions, which will create an electric field in your material. And this electric field can couple to your electron. And you can derive an expression for this, which is what Fröhlich did. So you can find that the electron-phonon coupling matrix element is proportional to 1 over Q. And this will become important later on. So let's now look at the exact computational techniques I will be using. And let me give you a crash course in density functional theory in about 3 slides. So bear with me. So in order, the basis of all properties is given by the foundation of quantum mechanics. It's given by the Schrödinger equation. So this is a many-body equation, and that once you solve this, you can obtain all properties of your physical system. And in order to do that, you need to know the many-body wave function, which typically depend on 3n spatial coordinates. So you have 3 Cartesian coordinates times n particles. But unfortunately, as you are well aware, as soon as you have a few particles, it becomes impossible to solve this exactly. So we will have to use some approach to tackle this, especially in a real solid-state material where you have a lot of electrons. So the way to do this, to solve this problem, is given by density functional theory, which was devised by Walter Kohn, who used to be at the University of California, Santa Barbara, and who got, for his contributions to density functional theory, he received the Nobel Prize in Chemistry in 1998. So what he did, together with Pierre Hohenberg, is that he came up with the idea that it's actually not the many-body wave function you need to know. It's sufficient if you know the many-body density. And your density only depends on 3 spatial coordinates instead of the 3n spatial coordinates you had before. Once you know the ground state density of your system, you can obtain any of the other physical properties as a functional of the density. So functional is just a function of functions. Okay, so now we know the density is a key quantity, but still we need to solve a many-body problem of interacting electrons in some kind of external potential, which is still a very burdensome process, which is nearly impossible. So again, this is where Walter Kohn together with Louis Sham enters. So he came up with the idea to replace this difficult many-body problem, to replace it with a fictitious system. A system in which you have non-interacting electrons moving in some kind of effective potential. But the key consideration you have to make is that you need to make sure this fictitious system has the same density as your original system. And once that's true, once you solve for the non-interacting electrons with the same density, you can still recover all of your properties. And those are, so what you need to do is solve these Kohn-Sham equations, which I'm giving here. So now you're solving for non-interacting electrons moving in an effective potential. And this effective potential contains all of the external potentials. It contains typical Hartree term and this exchange correlation potential. And this is where the problems start. So up to now, everything you have been doing is exact. There are no approximations made. But unfortunately, we don't know the true form of the exchange correlation potential. We can come up with different approximations to it. And that's where the alphabet soup of DFT enters, where you have all kinds of acronyms that signify different approximations to the exchange correlation function. You might have seen them in papers. You have the local density approximation, the generalized gradient approximation, and so on. And each of those exchange correlation potentials has its own strengths and weaknesses. But once you know what those are, you have a workable method which you can use to calculate electronic properties of your system. And if you go into a perturbation theory, you can also get the phonons and the electron phonon matrix elements. So in short, you can get all of the terms that entered in this Fermi's golden rule equation for the absorption. So that's the techniques I will be using on the material of tin oxide. So tin oxide, I'm showing you the unit cell here. The gray atoms are tin atoms. The red ones are oxygen. And this is the rutile structure. So you only have 6 atoms in the unit cell. But it's important to know that this is not an isotropic material. The so-called C-axis will be important. Your properties depend on if your light will be polarized parallel to C or perpendicular to C. And now for those who are more familiar with the technical details, I will be using norm-conserving pseudopotentials in a plane wave basis set. I will use the local density approximation, and everything will be based on the quantum espresso package. So I will also calculate Q points, so the phonons on a dense grid, and use that to calculate the absorption. So let's have a look at what our results are. So if we go through this whole process of solving for the absorption coefficient, we get the following results. So what I'm showing here on the y-axis is absorption cross-section. And this is simply the absorption coefficient divided by the free carrier concentration. On the x-axis, I'm plotting the photon wavelength. And if you're not as familiar with wavelengths in nanometers, at the top I'm just showing a schematic picture of what that corresponds to in terms of the visible light. So as I said before, tin oxide is an anisotropic material, which is why there are 2 different curves here. What you notice immediately of this plot is that you have a linear behavior for a large range of photon wavelengths. And because we're working, I plotted this on a log-log scale, that means your absorption cross-section follows some power law. So in fact, if you would fit the linear section, which I did, which is these dotted lines, you can find that this is a power law where the absorption cross-section is proportional to the cube of the photon wavelength. So this is purely based on our first principles results, but we can actually explain why this is a cube power. In order to do that, I will revisit Fermi's golden rule. So this is, again, the full formulation where the S1 and S2 are given by this. But just to make things simpler to follow, I will just look at the energy dependence of the different terms in this expression. So we have that the absorption coefficient is proportional to 1 over omega. So that's our first energy dependence. So the next one occurs in this S1 or S2 terms. We have a dipole matrix element, which depends on your momentum. And through the energy momentum relationships, your dispersion relations I showed you earlier, we can relate this to an energy. The same is true for your electron phonon matrix element. They depend on your momentum, and thus they will depend on your energy. And it's very easy to see that the denominator, you have this difference between eigenvalues. This is also an energy term. Keep in mind, we are taking the square of this, so then we get this formulation. And the last term that depends on energy is this delta function. This is density of states, which depends on energy as well. So let's now try to come up with an approximation for each of those different terms in function of energy. And to do that, we have to have a closer look at the band structure. So it turns out for all of those transparent conducting oxides, the band structure looks the same. You have this really dispersive conduction band. And if you look close to the gamma point, the zone center of your system, this is really a parabolic equation. So this is the dotted line. This is a parabolic curve. For larger momentum, it's almost linear. And you can combine both of those behaviors in one simple hyperbolic formula. So you can show that the square of the momentum is equal to the sum of the energy plus some term that will indicate how much your band structure is non-parabolic, and then the square of that energy. So in case your energies are small, you can neglect the last term and you recover a parabolic behavior. If your energies are large, you can neglect the epsilon term because the epsilon square term will be much larger, and you get a linear equation. So for the region of energies we're interested in, it's therefore a good approximation to write the band structure, the energy dispersion relation of the bands, as a linear equation. Okay, so if we make that assumption that your bands are linear, we can rewrite some of those terms. So your dipole matrix elements can be rewritten in function of velocity matrix elements, which are just a derivative of your energies with respect to your k vector. And because we have a linear relationship, this will become a constant. At the same time, you can calculate for linear bands that your density of state is quadratic. So now we have functional forms for dipole matrix elements and for the density of states. So the one remaining term is this electron phonon matrix elements. And that's where this earlier mentioned Fröhlich model comes in handy. Because if you remember, it said that your electron phonon matrix element is proportional to 1 over your Q. So the square of it is proportional to 1 over Q square, or proportional because of your linear relationship by 1 over energy square. So now we have expressions as function of energy for each of those terms. You can simply combine them, and we find that the absorption coefficient is proportional to 1 over the cube of your energy, or if you want to express this in terms of wavelengths, that your absorption coefficient is proportional to the cube of the wavelengths. So that explains the power law. So that explains this whole range. But you might notice for smaller wavelengths, you get significant deviations from this power law. So what's going on there? So let's have a look at those processes that are in the UV region, where they take place in our band structure. So this is the same band structure where I overlay the rainbows of colors. So you see in the UV region, you're either the conduction bands over here or at the edge of the Brillouin zone, where you also have the second conduction band contributing. And since our absorption coefficient is proportional to the density of states, we will have a much higher density of states once you reach those points near the zone edge. And indeed, if you just plot density of states, you see a strong increase, and this increase in the availability of final states translates in an increase in the absorption. So far I've discussed the behavior of the absorption coefficient over a wide range of photon wavelengths can be given by the cube of the wavelength, and I explained to you why there are deviations in the UV region. So let's try to get even more insights into those absorption processes. So for example, this Fröhlich model, how accurate is this? And other questions we can ask is, what kind of phonons are most important? Is it just longitudinal optical phonons or also acoustic ones? And finally, we can ask ourselves, which process will be most important? The emission of phonons or the absorption of phonons? So let's have a look at that. So first of all, what I'm plotting here is again absorption cross-section as a function of photon wavelength. And I'm plotting our previous results obtained using first principles with the black curve. The red curve, using the same data, but replacing the calculated electron phonon matrix elements with this Fröhlich model. And so you see that for a wide range of photon wavelengths, especially for large photon wavelengths, this model works really good. But it completely misses this increase in absorption for lower wavelengths, and there are several reasons for that. First of all, the Fröhlich model only works for longitudinal optical phonons. So maybe other phonons also play a role. And it also assumes that the electron phonon matrix elements have this 1/q dependency, which also might not be accurate for the whole range of energies. Let's first look at different phonons that contribute. So what I'm showing here is a phonon spectrum. So this, instead of electronics information, contains information about the phonons. So again, it's energy dispersion relation, but for the phonons. So on the y-axis, I'm plotting the phonon frequency, and on the x-axis, it's again momentum. Because we have 6 atoms in our unit cell, we will have 18 different phonon modes. Of those 18, there will be 3 acoustic modes, which just correspond, if you look at the zone center, to rigid translations of your unit cell. And you will have 15 optical phonon modes, and several of them will be longitudinal optical phonons. You might also wonder why you have those discontinuities at the zone center. And this is due to the anisotropy of your system. Different phonons have different energies in different directions. And that's just indicated by those discontinuities. Okay, so let's subdivide our total absorption and subdivide it by the type of phonon that's actually contributing. So in this case, I'm now plotting the total contribution of certain phonon modes. So the red curve is only for longitudinal optical phonon modes, while all other phonon modes are in the blue curve. So you immediately see that for long photon wavelengths, it's mainly longitudinal optical phonon modes that contribute. But for smaller wavelengths, it's the other phonons that become important. And this also gives you an idea where you can expect to be able to use the Fröhlich model. exactly the region where the longitudinal optical phonon modes are actually the dominant contribution. So we can also look not just at the phonon modes, but you can also look at the electron phonon matrix elements themselves. So that's what I'm plotting here, the electron phonon matrix elements for two different directions in your momentum space. So the first, from gamma to x, is a direction perpendicular to the c-axis, while from gamma to z is parallel to c. And I'm plotting only the modes that have significant electron phonon matrix elements. So as you expect, you see that it's mainly longitudinal optical phonon modes that actually couple to your electrons. But what's kind of surprising is that there is another mode independent of the direction that also couples rather strongly to your electrons. This A1G mode is a so-called breeding mode. So in this mode, your oxygen atoms are moving in and out of your cell, and this also leads to a strong coupling to your electrons. Okay, so let's look at the different processes. As I mentioned before, you can always either emit a phonon or absorb one. So if we compare the absorption cross-section as a function of the type of process that's involved, and we're doing this at room temperature, we find that it's mainly emission of phonons that's dominating this absorption. The absorption of phonons is much smaller contribution. And the reason for this lies in the phonon occupation numbers. If you write down the phonon occupation numbers, in case for the emission process, you have that this is proportional to phonon occupation numbers plus 1. While for the absorption of phonons, it's actually just the phonon occupation number. And this has dramatic consequences. So for example, if you would lower your temperature in order to try to get rid of your phonons, you will still have absorption, because you can always, even at 0K, you can emit phonons. And that's the dominating process. So this really is a fundamental limit of your transparency in those materials. So let's quickly recap this. It's mainly, LO phonon modes contribute mainly to larger photon wavelengths, and it's mainly the emission of phonons that's the main process. So in the final part of my talk, I want to look at some device implications. I want to look if there are any other kind of process that can give you additional momentum. And I want to have a quick look at the different material.
Well, so before you get to the fundamental limitations, yes, there's coupling constants in there that determine the strength of the coupling. Mm-hmm. So your discussion has been qualitative about the trends. Yes. But then there are, what can you tell us about what determines the strengths of the coupling? So in case of longitudinal optical phonon modes, it's really this electric field that's created by the motion of the ions. In case of this breeding, that's a plasma frequency, right? That's basically what's called a plasma frequency in the rest of it. Yes. Okay, but then you've got all these other ones which are cutting it off at the bottom end and coming in, and so. Is there some materials that have small coupling to the phonon modes? And then there would be limitations you're indicating here?
So yes, if you go to different materials, we'll have different coupling to do the phonons. So in fact, in just a bit, I will look at a different material and we'll show that this will actually lead to smaller coupling. So I'll get to that. So let's assume we have an optical device, for example, an LED, where our top contact is a transparent conducting oxide of, let's say, 5 micrometers thick, with a carrier concentration of 5 × 10⁻20 carriers. So if we use our results, we find that for the visible region, we have about 2.5% absorption. So not too bad. That's why it's a transparent material. But if you go to the UV region, this increases to 12%. And if you go to the infrared region, where you have this power law, the larger frequencies you look at, the more absorption you will have. For example, if you would look at a typical wavelength of 1.5 micrometers, you will get up to 40% absorption, just because of the phonons. Of course, there are other processes possible that will also give you the momentum you need to reach some final state. And one obvious process to look at is this by scattering by charge impurities. Because remember, in order to get free carriers, we actually have to dope our material. We need to introduce atoms that will donate their electron to the conduction band, but those atoms will remain charged, and they can scatter electrons as well. So in case of tin oxide, people usually use fluor doping to get the high carrier concentrations. So in order to model this scattering from those charged impurities, we'll use simple screened Coulomb potential to model this. And in the following, we'll make a simplifying assumption. We'll just assume that all our dopant impurities are fully ionized, and that each dopant impurity gives rise to exactly one free carrier. And of course, in reality, there might be compensating defects that will also be charged, and that would lead to even more scattering. So this is an underestimation of the scattering. All right, so let's compare this for some different levels of charged impurities. So if we have 10 to the 19 impurities, we find that it's mainly phonons that dominate your absorption. So that the previous results are shown in red for phonons. The black curve is the result for impurity. And you see it's at least an order of magnitude smaller for all photon wavelengths of interest. Of course, we want to have really high free carrier concentrations. So if you go to 10 to the 20, you actually see that both processes become comparable in size. And if you further increase your charged impurities, it will be charged impurity scattering that will dominate your absorption. All right, so let's have a look at a different material, because maybe this is all just specific to tin oxide. So in order to do that, we'll have a look at indium oxide, which is probably the most widely used transparent conducting oxide. So in order to get carriers in this material, people usually dope it with tin, and then you get indium tin oxide, or for short, ITO. So this is the unit cell of this material is much more complicated compared to the tin oxide unit cell. It has this so-called Bixbyite structure, where your indium atoms are in the center of distorted octahedra, and in your whole unit cell you will have 40 atoms. It also means you have 120 different phonon modes, which first of all increases the computational cost significantly, but also makes it much more difficult to really distinguish contributions of specific phonon modes. So if we look at the electronic band structure, we see it looks very similar to that of tin oxide. Again, you have this highly dispersive conduction band, and that's because also in this material, it's mainly S states that contribute to it. Your valence bands are again really flat, and that's because they consist of oxygen p states. And the band gap of this material is 2.7 eV. So let's compare the total absorption cross-section, only taking into account phonons for both materials. So the green and blue curve are the earlier results for tin oxide, while the purple curve is the result for indium oxide. You immediately see the absorption is smaller, independent of the photon wavelength. And this occurs for several reasons. So first of all, indium oxide actually has a smaller effective mass than tin oxide, which causes the density of states of your conduction bands to be much smaller. And because your absorption coefficient is directly proportional to your density of states, this lowers your overall absorption. At the same time, indium is a much heavier ion than tin. And this means your LO phonon frequencies will be much lower in frequency. And at the same time, because indium oxide is slightly less ionic, which means you will have smaller dielectric constants. And if you look at the Fröhlich model in closer detail, you will see that it also says that your electron phonon matrix elements are proportional to the square root of your longitudinal optical phonon frequency, and in case of indium oxide, this is smaller. It's also proportional to this difference in dielectric constants, and this is also smaller in indium oxide. So both of those will decrease your electron phonon matrix, your electron phonon coupling matrix elements. So I think that answers your question you had earlier.
Well, we don't know why. It's smaller, but it'd be nice to know why the couplings are smaller.
Well, in this case, I'm just looking at longitudinal optical phonon frequencies. It's
So is it the dielectric constants? And it's a combination of the dielectric constants, the effective mass,
and
everything all put together?
Yes.
Is it? And then you could fit this curve with the Fröhlich model all the way across.
Mm-hmm.
What happened to the longitude, to the other modes? Why don't they couple?
So they will couple, but in case of indium oxide, this transition point where you have the second conduction band available is at much higher energies. So you won't be able to reach this within this energy range. And it's mainly those transitions that require the other phonons. Okay, so let's conclude. So I hoped to have shown you that indirect absorption can be described from first principles, and that this is really an important process in transparent conducting oxides. So I showed that in general, for a wide range of photon wavelengths, as long as you don't reach those other conduction bands, it's mainly dominated by longitudinal optical phonon scattering, and can be given by this power law, where the absorption coefficient is proportional to the cube of the wavelength. There are some deviations, and usually those are due to band structure effects. In case of tin oxide, you can reach this second conduction band. It's also important to note it's mainly emission of phonons that dominates the absorption. Even at low temperature, you will have this absorption process. As soon as you introduce charged impurities, this will also become important if your concentration of charged impurities is larger than 10 to the 19. And also compare this to indium oxide, which had much lower absorption across the whole range. And with that, I'd like to conclude, and I thank you for your attention.
Okay, Iris. Julie?
So in ITO, right?
Yes.
Indium doped tin oxide
Mhm.
definitely is so far the best TCO,
Yeah.
right? So with the probably smallest absorption,
Mhm.
highest transmission. But in addition to that, you'll have very low sheet resistance.
Okay.
So, but we know that indium is scarce, so you just have to find another element to replace it because it's not enough for us to
Yeah.
make all the solar cells. So from your simulation, do you have suggestion to say, all right, some element or element with this kind of property would probably generate a similar result?
So that's actually a very difficult problem. So because it turns out indium oxide has this really small band gap. Your band gap in first order is also proportional to your effective masses. So that's why it has these low effective masses, because this band gap is actually 2.7 eV would actually lead to absorption in the visible as well. But in case of indium oxide, transitions from the top of your valence band to your conduction bands are actually dipole forbidden. So you need to go to lower state in order to have dipole allowed states. And that's a property you don't find for any of the other transparent conducting oxides. You don't have it for tin oxide, which has a larger band gap, larger effective masses. Also zinc oxide is probably, it's better than tin oxide, but it can't beat indium oxide. So it's a trade-off you have to make between expense and transparency, and also depends on what carrier concentrations you're looking at. Because in all those results, you have to multiply by your free carrier concentration to get the actual absorption. So if you can keep that low, you will also minimize your absorption. Yes.
Very nice talk.
Thank you.
I have a question regarding, for example, data science and now these big data methods where in chemistry, for example, they are applied to design molecules that have specific properties.
Mm-hmm.
Do you think this kind of field also could be applied to the design of these materials that you're looking for?
So what you can, so those calculations are very expensive, so you can't just run them in a high throughput way. But what you can do is use this simpler Fröhlich model and use that to test a wide range of materials.
Right, but at the moment, that's pretty much what is happening in chemistry. I know that DFT is a very expensive method, and some people are creating these databases, and then based on those databases, they are taking the extrapolations that goes not what the machine is doing, but it's in principle from the engineering perspective. They are able to match the design or the qualities or properties they're designing, and then they do the calculation with DFT or something that actually validates the computer.
Yes. So in this case, what you would be looking for is a material that has low effective masses, which is something you can easily calculate using DFT, but which also has large enough band gap. There you need to already make sure you use an appropriate method to actually correctly describe your band gap. And you need to make sure transitions to the second conduction band are also, there's a large enough energy separation. Because if that's not the case, you will still get even larger absorption. But those guidelines you can use and then look at your database, screen for the different materials, and then for the ones you think would be good enough, you calculate dielectric constants, you see what you would expect for electron phonon matrix elements, and then only then you can do a full calculation to actually check this. So does that answer your question, or?
I have a question.
Okay.
Do you have to consider the contribution from the impurity levels to the absorption?
So
I wonder where are those levels?
So in this case, all of those materials, you're shallow donors. So your actual impurity level will be somewhere resonant with the conduction bands. So it's not in the gap, so you don't have to worry about it.
And can you compare, I didn't see how you compare the curves with the experimental results. So have you made those kind of comparisons?
So yes, that's a very good question. So we try to do this for tin oxide, but apparently there's some experimental constraints of really getting accurate absorption coefficients in this wide range of energies, only due to the free carriers. But for zinc oxide, for example, people also find this wavelength to the third power behavior. And we can explain why that would happen as well.
Can you match the numbers too? I mean, the trend, I think it's easier, but can you match the cross-section you calculated with the measured values of cross-section?
I actually haven't tried comparing the absolute numbers. So for some of the other absorption I have been looking at, for example, direct free carrier absorption. In some materials, the second conduction band is not high enough, so we can also have direct transitions to that, and that matches experiment really well.
At the very beginning, we see one application was for putting this transition transparent conductor materials for the box solar cell.
Okay.
Is it for like the collecting carriers when we separate the
Yes, exactly. It's to collect your electrons.
Okay, so it's how about hole? Because what I understood is for electron they have a sharp dispersive, as you said.
Yes.
So it means electron could be mobile easily, could be transferred. It's a low mass. But hole has like a high like effective mass.
Yes.
So at solar cell we separate electron and hole. We like to collect both of them.
Okay, yes, that's a very good question. So those materials are typically used only to collect the electrons. So the electrons will go to the conduction band and can be rapidly extracted. In order to collect holes, you need to have a material that has a much, where the valence band offset is so that your holes would actually go into the material. And that's not the case with those materials. You can't use them. Your holes will never go there in the first place, and even if they would, their mobility will be really low. So the answer is you need different materials for that. But in a solar cell approach, for example, you can use a material that does absorb if you put it at the bottom. It's only the top contact that needs to be transparent.
Okay, any other questions? If that's not the case, let's thank our speaker.